So, hello everyone. So, what we are going to discuss today is the mind map of laws of motion. In the previous one, we discussed about kinematics and scalar and vector, in which we discussed that how things move and from rest how things start to move. But in this chapter, we will fundamentally discuss why they move or why the motion changes, move or stop, or what is the reason behind the change of velocity and all those things, acceleration. Those we will discuss in this one. So coming back to this mind map, first what we will discuss is inertia, both these type of inertia. What inertia is actually, let me just expand it. Yes, for example, let's say there is this person who is at rest. Now this person is at rest. If you want to move it, then you will have to apply some force, and that force must be significant. That means there is some resistance to move, right? Resistance in the body to move. This type of inertia or this resistance has another term called inertia of, what is it, at rest, right? Inertia of rest, which is actually equal to uh, in numerical terms, inertia is actually equals to mass, actually, because the heavier the object, the more the force will be needed to make the object move. In the other case, this one was at rest. Now in this one, this person is moving with respect with the maybe 5 meter per second in this direction. Now what happens is, if it wants to change its velocity, or let's say you want the person to stop, so what you will do is probably apply some force so as to stop the person from moving. But what will happen is actually, yes, so what will happen is, the force you are applying, why is it that you're applying a force? It must mean that there is this some resistance in this body, resistance towards stopping or towards resistance for stopping. It means it wants to continuously move in that particular direction with 5 meter per second, whatever velocity it had initially, till infinite time. It is happy to do that. The moment you want the person to stop or maybe change its velocity, then the person will face some resistance inside it. That resistance we call as inertia of motion. Inertia of motion means the resistance of the body to continue in that motion, whatever motion it had. All right, so we discussed about inertia, inertia of motion and inertia of the body, and this is the general definition of inertia. And what we will discuss is the most important part for this chapter, which is the theoretical, uh, maybe fundamental basis, you can say, for maybe a large chunk of physics. The first thing says is actually what we discussed initially about inertia is the same as the first law of Newton. Newton gave three fundamental laws for motion. The first law says that whatever motion it was initially continuing, for example, this person was at rest, and for example this person is at with having some velocity v in any direction. All right, so motion, this law says that unless until you apply some force on this body, this person or this object will continue to be at rest till infinite time. In the same manner, if it is continuing with some velocity v which is constant, then that person will uh, continue to move in the same particular velocity v unless until you apply some force over it. So fundamentally, what this first law says is that you have to apply force so as to counter the impulse, the inertia of the motion or inertia of rest. So you must, force is must to tackle inertia. You can write it, tackle inertia, if you have clearly understood the meaning of inertia. The second law says actually is that, first of all, you told me that there must be some force. What should be that force? Is it that any amount of force that I apply on this person on rest, it will cause the body to move? It is not so. Actually, the force that is applied, force is directly proportional to rate of change of momentum, of change of. Now, there is this thing that came up, momentum. If you don't know, momentum simply put is nothing but mass multiplied by the velocity. If the velocity is a vector quantity, it means the it is represented by small p or capital P anyway. So p also is a vector quantity, which is momentum, and it must have the unit of kg meter per second, since it is the multiplication of mass and mass. So anyway, this was about someone who didn't know about the momentum. Uh, this law, second law of motion, or Newton's second law, actually says that force is directly proportional to the rate of change of momentum. What does it mean? Rate of change of momentum, rate of anything. Let's say there is this quantity x. What is the rate of change of x? It must be equal to dx by dt, because generally if we see a term written as rate of change, it generally is in terms of time. If it is in terms of any other quantity, they will just let you know, but if it is not mentioned, it is with respect to time. So rate of change of momentum means dp by dt. This must be proportional to force. All right. Now what we have here is, uh, yes, this is the basic uh, Newton's second law of motion. We will change the color so as to distinguish. Yes. Now what we will do is a little bit expansion of this one. What is actually, first of all, momentum? This is mass multiplied by velocity. So p is equal to mv. What if I want to find differential of this? Then I will have to do this, and dp is equal to, in general physics, what we have is mass is always constant, right? Mass of a particular object or a particular particle is always constant. Only in nuclear physics and all, we have variable masses, but otherwise mass of the object remains constant. It may get distributed into different objects, but the overall mass remains the same. If something which is constant is inside the differential, we can conveniently take it out to write it as, right? So dp is equal to nothing but mass into dv. Can we replace it here? Of course we can. So dp by dt, actually what we will do here is another thing. We will convert the proportionality into equality, such that there must be some constant into f, right? So this is the basic thing that we always do, proportionality into equality, and we apply some constant. But for the sake of convention, or for the sake of simplicity, what we take is always c is equal to 1 here. So dp by dt is actually defined as force. Now we plug this value here. What we will get is, just a second, yes, what we will get is dmv by dt is equal to force. So what we have is, you can take the mass out, m dv by dt is equal to force. We can write it as in the vector form, no problem. And what is dv by dt? I think in the previous mind map we have already discussed that dv by dt is nothing but defined as acceleration is equal to force. So here we got the simplified version of second law of motion, Newton's second law of motion, which is nothing but force is equal to ma, that you always apply, nothing else. So that was the second law of motion, Newton's second law of motion. And there is this third law of motion, which actually is a um, maybe you can say application of the fundamentals of Newton. What it says is, to every action there is always equal and opposite reaction. But I just said equal and then I said opposite. It doesn't mean equal in terms of vector. What it means is equal magnitude and opposite direction. Since we are talking about this action, what is this action? Action is nothing but force. Newton just wrote it in a fancy form, but these terms, action is actually representing force, nothing else. So what we have here is, from this thing, if you have a block here which is on the ground, and you apply some force, or maybe you apply the force here directly on the ground, let's say F, what you will have here is the magnitude F and direction downwards. Then with the same amount of force, the ground will push you in the opposite direction. This magnitude will be equal to this magnitude. So this is the meaning of, to every action there is equal and opposite reaction. Reaction means what you applied was action, and what the ground did to you in return was reaction. So this was the third law of motion, Newton's third law of motion. Now, this has been done. Let me just take it up. This has been also done. Inertia, 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 done. Okay. And did we discuss about momentum? We can quickly go through it again. The momentum was nothing but mv, right? Or mu, whatever you write the velocity. Let's say, and this is for a single particle, right? Single particle. But what if I have particles? Two particles. This one has a mass m1, this one has a mass m2, this one has a velocity u1, this one has a velocity u2. Now, this second law of motion that I discussed has a consequence here. What the consequence is actually, let's say, or maybe I can just take one particle for now, and in the second case I will take the two particle system. For one particle system, this has a mass m1 and u1, and this was dp by dt is equal to force, right? What if you don't apply a force on this body? What will happen to the momentum then? What if this is 0? Then dp by dt is equal to 0, which means there is no rate of change of momentum, means momentum is constant, which means that this body, whatever momentum it has, it will continue with the same momentum till infinite time, unless until some force is acted upon it. So this was the basic thing. What if I take two bodies in a system? In a system means whatever quantities I have, I can take the sum of this box. I can look into what is the net force being acted on the box, what is the total momentum of particles inside the box, and things like that. What is the total mass of the box? The box is a separate entity here. So what this system says is, if there is no force, external force acting on the body, then the net momentum, total momentum of the system means the system of particles, should remain constant. should remain constant. What it means is the net momentum m1 u1 plus m2 u2 should be constant with time. It should not vary. And what if I consider that this one was moving in this direction and this one was moving in that direction, and it happens that it collides with each other? What will happen in that case? Actually, whatever during the collision, let me just zoom it out. During the collision, this object will apply force on the second object, and the second object will apply force on the first object in the opposite direction. But overall, from the system, do you think it is some external force? Of course not. It is internal matter of the two bodies. So F external is again zero here. But if external is zero, what it means is that momentum of the system should be zero, should be constant. What it means is, let's say the velocity initial was u1 and the velocity final becomes, let's say, v1 and v2. What it means is the m1 u1 plus m2 u2, this is the initial momentum. And what's the final momentum? Since it has the final velocity of v1 and v2, m1 v1 plus m2 v2 is equal to final momentum. But since I just told you that the collision is internal in nature and no external force has been applied, because the collision of two bodies are internal matter of both of them. There is no external force or external hand which has pushed the bodies. So internally of the total system, momentum of the total system should also be conserved, which means these two quantities should be conserved. m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. This is the law of conservation of momentum. Law of conservation of momentum. When do we apply that? Only when the net external force on the body is zero. If there is some external force, you will never apply the conservation of momentum. So I hope that is clear from my side uh, about the momentum. The product, this was already explained to you. Sorry. And this has been explained to you as well. Now, um, coming to the force, coming back to the force, or maybe I can use this space here. Yes. Now, there is this object and it is at rest. What if I push it with a force? Of course, from the second law of motion, you have learned that it will gain some acceleration, due to which it will tend to move the object. But what happens if I apply another force equal and opposite from the other side? Let's say from the force this one, acceleration a1 towards downward is resultant, and from the force f2, or actually it was the same force, right? F1 itself, the same magnitude force, it will tend to accelerate with the same acceleration upwards. But a, uh, sorry, a particular particle should not accelerate with two different accelerations at a particular instant, right? It should always have the same acceleration. What it means is a1 downwards is equal to a1 upwards. It means x is equal to minus x, nothing else. Only in the case x is equal to 0, this condition will be satisfied. It means when you apply two opposite forces to the system, what it will result into is net force is equal to 0. You can also see this in the form of vector quantities. If you have two opposite vectors, if you add them up, the net resultant vector will be 0. So, and if the net force is equal to 0, acceleration net should also be 0. It means it should remain at rest. It was initially at rest and it should remain at rest. What we call this particular situation is nothing but equilibrium. Equilibrium. Equilibrium does not mean that no force is being applied. It only means that the net force being applied on the body is zero. You could have several components in which the vector addition of all of them must be zero, and you can also have another case in which there is no force actually being applied. In both of these cases, there will be no acceleration of the system. In other words, it will be in equilibrium. All right. What if I have another object which is moving in this direction with a velocity of 5 meter per second? What if I apply the same two forces here? Let's say 10 Newton and 10 Newton. What happens then? Is it going to be in equilibrium? Actually, it will be, because the net force being applied is again zero, which means it should not have any acceleration and it should be in equilibrium. Equilibrium does not always means that it should be at rest. Equilibrium always means that it should continue with whatever state it was initially having. The motion should not change whatever velocity it has, or the condition of rest should not change. That is the meaning of equilibrium. Equilibrium is not always the same as rest. All right. So this was the concept of equilibrium of forces. This was the equilibrium of forces. Now we have something called friction, or maybe yes, we should. I think we should deal with friction first so that it is easier to understand these. Um, I can take it up here. All right, friction. What is friction? Let's say you have this block and you want to move it. If it is very heavy, you will have to apply a huge amount of force. But where is the force going? If you apply a small amount of force, it does not move. Why is it so? It should move, right? Whatever quantity of force, let's say it is having 100 kgs, and you apply 1 newton, it should at least accelerate with 1 by 100 meter per second square. But it does not accelerate at all. It does not move unless until you apply some significant amount of force. Why is it so? Because this body experiences some friction. Friction is nothing but resistance from motion. It is not the same as inertia. Why? Because this resistance is variable. It is not just that it is having some mass and that's why it is difficult to move. This resistance can change as per the direction of force. Let's say it is in this direction currently. When I'm applying the force in that direction. But what if I apply the force in this direction? Sorry, I apply the force in this direction. Actually, what will happen is the the friction force which will actually come up in the opposite direction, which means friction is always trying to cancel whatever effort you are putting to move the system or make the system accelerate. All right. So this is friction. Now, in layman terms, what we said was the more the mass, the more the frictional force. But it is actually more dependent on frictional force is directly proportional to the normal force, not the weight of the object, but the normal force. What is the normal force? Due to the weight, with the, let's say this is a 1 kg body, and the ground pulls it towards the center of the earth with 10 newton, but it does not move, right? If it was being acted by a 10 newton force, it should have moved. But there is another force which the ground applies in reaction to the force being applied by the gravity. That is because of the Newton's third law of motion. So that some 10 newton force is also acting upon the block in the upward direction, so that the net force on the block becomes zero and it remains at it remains stationary. We always take the normal force. Some might argue that if it is the same, why can't we take that? Why can't we take the weight itself? Because this these are equal in the cases when the object is not accelerating in the y direction. But once the object starts accelerating, we will learn about them in later classes, or maybe you can solve problems based on that. You can observe that the based on uh, vertical accelerations of the body, you can have different weight and normal forces, but the friction force always depends on normal force, not the weight. And if I convert this into equality, the frictional force is nothing but equal to some constant into normal force. What is this constant? It is called as coefficient of friction. Coefficient of friction. And actually there are there are basically two types of coefficient of friction. One is called static friction, which is represented as mu k, and there is another called kinetic friction. Kinetic friction, which is represented as mu. Sorry, this was static, and this is kinetic. This is in motion, when the object is in motion, and this is stationary, rest. All right. Your mind map also discussed about something called rolling friction. Actually, rolling friction is nothing but static friction and kinetic friction only. In later classes, in the rotation chapter, we will discuss that the body, if it is rolling, there are two types of rolling: pure rolling and impure rolling. In pure rolling, it is actually in the form of static friction, and in the impure rolling, it is in the form of kinetic friction. So uh, your mind map has given it in a separate form, but it is nothing but just this rolling friction is nothing but sometimes kinetic friction and sometimes static friction, based on whether it is pure rolling or impure rolling. And the thing that is important here is, I can draw a graph here. um, this is the frictional force, and this is the force being applied. Force applied, what it means is, it always uh, it is always proportional until a certain point, after which it slightly declines and continues to be constant. What this actually means is, if you have, let's say, 10 kg of body, and you apply some force. Let's say you have applied a very small amount of force and you are gradually increasing the force. uh, what we discussed here was friction force was nothing but mu into k. Let's say we can take 0.1 is equal to mu static. So, and what will be the reaction force here? Reaction force will be the 100 newton, what it has on the ground. So mu into 100, which is nothing but 0.1 into 100, that is 10 newton, which is equal to mass into acceleration. Mass is equal to 10 into acceleration, so acceleration becomes 1 meter per second square. Now this is the this 10 newton is the maximum amount of frictional force which can be generated. If you apply only 1 newton on the object, the frictional force acting on the body will only be 1 newton. It will not be 10. It will be 1 only. Whatever is needed to counter the uh, force that I am applying. That is why it is given as straight line until this point, at which it is reaching the maximum, after which it becomes constant. But there is this slight dip that you can observe, it is because of uh, mu static is slightly bigger than kinetic, because once the object starts moving, uh, it actually it actually faces less resistance from the body with respect to when it was at rest. Because if it is object is at rest, then intermolecular forces are strong because of less distance between the two surfaces, and that's why the it is slightly more difficult to move. So that is what we discussed here, that how to with the example, also we discussed that how to calculate the maximum amount of frictional force that can be there. And frictional force is not constant, but it varies according to from 0 to maximum force, maximum frictional force which is possible. And there is this small dip because of this slightly higher value of mu k, mu s. Until now, until this point, mu s was acting, the friction, static friction, and from this point onwards the kinetic friction starts acting. Now if this is clear, we can move on to the next part, which is, just a second. That was I was talking about limiting friction. Limiting friction, and these has been covered. So what we are left with is two very particular, maybe we can call it even problems. I think this one has not been covered, right? The centripetal, we can take it up now. After that we will look into the two examples that we have. The Let's say you have a pebble. This is the pebble, and this is the fixed point, and this is the string. What you do is you can hold it up with your hand and start to rotate this body. It will of course take the shape of a circular motion or circular trajectory, with the center on this one and the radius equals to the length of the string. But what is happening over here is, maybe you are doing uniform motion, uniform circular motion. Do you think uniform circular motion is any uniform motion, any other uniform motion? No, actually, because even if it has a constant speed, let's say it has a constant speed of u, it is moving in this direction at this instant, it is moving in this direction at this instant, it is moving when it reaches this part of the trajectory, it is moving in this direction. So even if the speed is constant, you see that the speed is constant but the direction is changing. And velocity has two components: magnitude, which is which is nothing but speed, and the direction. If direction itself is changing, it means velocity is changing. And if velocity is changing, it must mean that it has some acceleration associated with it, right? So acceleration, what it has is actually, we call it centripetal acceleration, because what you're basically doing is pulling the body. You must have experienced that when you try to rotate the object, you continuously actually try to pull the object towards you. You do nothing else but you just give it speed in the initial part of the motion, and then after that you just try to pull the object towards you continuously, so that it follows a circular trajectory. This towards the center force, a force towards the center, is called centripetal force, or which actually results into centripetal acceleration, which is defined as v square by r. R is the radius here. And if you talk it about, or if you talk it in terms of angular velocity, first of all, what is angular velocity? We can understand that in terms of what is first of all this velocity, this translational velocity, which is nothing but dx by dt or dr by dt, right? But angular velocity is nothing but the change in omega, or sorry, the change in theta, d theta, the change in theta with respect to time. In 1 second, how many radians it covers is actually equals to the angular velocity. And if you try to make a relation out of it, this dx by dt, I can also write it in form of r by r. What is dx by r? This is nothing but x. And if this is d theta, for small angles, do you know that this length is x is actually equal to r d theta is equal to dx, isn't it? You must be knowing, when you have a small angle, then this part of the circle actually becomes r into that small angle. And if you substitute here, what you will have is r d theta divided by dt into 1 by r into r. R gets cancelled out, and what you're left with is d theta by dt into r. See, v is equal to d theta by dt into r. And what was that d theta by dt? Change in angle with respect to time. I just called it angular velocity omega r, omega into r. So this is the relation which will be very very important. V is equal to omega r in any sort of circular motion. Even non-uniform circular motion, instantaneous velocity will be equal to instantaneous angular velocity into r. You can even write it as omega r the whole square divided by r, which will be nothing but omega r omega square r. So this is the centripetal acceleration, and you can find the centripetal force as well. Centripetal force, which is nothing but mass into centripetal acceleration, which is mv square by r m omega square r. This is the centripetal acceleration. And there is another thing called centrifugal acceleration, which many students get confused about. Is let's say this was the same pebble, or maybe uh, you are rotating an empty box in a circular orbit, and let's say you have placed a sensor or a person inside it. what Whatever force that you are pulling the whole system or the whole box towards you is nothing but centripetal force. But due to the circular motion, this object will, or this person will actually experience a force which will be outwards, uh, out of the, or coming out of the center, or in the direction opposite to the center. That is called centrifugal force. Centrifugal force. In magnitude, they are always equal. Actually, the centripetal acceleration and centrifugal acceleration are always equal. But there is a fundamental difference, that centripetal force is being acted by you, and centrifugal force is the result of that whatever you did in that system. You placed an object and you studied the force being experienced by the object. Now, coming back to, I think we have dealt with this one. And what we will discuss now is two particular problems: motion of a car on a level road and on a bank road in a circular motion. What this basically means is, let's say there is this track of circular design. Oh, sorry, it became very thin. And there is the radius of the track, and there is this car which is moving with some speed u is equal to speed. I'm not calling it velocity, because since it is covering uniform or non-uniform circular motion, its velocity is always changing, because the direction of the speed is also changing, direction of the velocity. So what you have to find here is, in the first case, what is the maximum speed with which the object can be moving, so that yes, if um, I think there was some embankment as well. What this embankment means is, first I told you that this body is moving in a circular track, but once you look into the cross section, this actually looks something like this. The car is here with its wheels moving towards you, coming out of the system, and this is the circular motion which is it is covering. This is the track, and the track is slanted. What you might think is, you have a road which is circular road, and the right side of of the road is actually sloping downwards, and the left side of the road is sloping upwards, and you still have a circular track. That is the thing that I'm talking about. Now, in this system, let's say it is moving with some speed u, and what you have to find out is, what is the maximum speed u, so that this object is remains in the circular track. Or what should be the u for, let's just call it u in this case, because the maximum and minimum will come up in uh, the next part, which is with friction, but this is frictionless. Mu is equal to 0. In this case, we are trying to find with what velocity should the object uh, move, or with what speed should the object move, such that it continues in that track and it does not slip down or upwards. All right. So for that to happen, what we will do is calculate the centrifugal force. Since it is moving in this direction, the centrifugal force must be acting in this direction, right? Because the circular track is this whole thing, and you are just moving in the circular track. So the centrifugal force must always act out of the center of the circular track that you are following. This is the circular track. Actually, if you imagine it large enough, it will actually be opposite. This is the direction of center, and this is the direction opposite to the center. And what's the what's the acceleration with which it should be, or what should be the force with which it should be moving outwards? The centrifugal force is equal to nothing but mv square by r, right? And this is the speed. But at the same time, there is this gravitational force also acting. I should use another color for this one. There is this gravitational force which is also acting on this body, but since it is moving in since this slope is having a very significant effect on this one, what I'll do is divide this one into these two components. Let's say this is angle theta. You have this one 90 minus theta, and this is the theta again, right? Maybe I should use a bigger diagram for this one, so that it's easy for you to understand. This is the yes, this is the car, and the centrifugal force is acting in this direction, which is equal to mv square divided by r. R is the radius of the, let's say this was the center of the track, the circular track. This is the circular track. All right. I think you can imagine it much better now. And this is the gravity which is acting on it. Since this is theta, and you can divide the acceleration due to gravity into two components, one which is parallel to the slope, one which is perpendicular to the slope. Since this is theta, this must be 90 minus theta, and this must be theta again, which means that this must be g cos theta and this must be g sin theta, these two components. Now what we have over here is um, you can also, what you do is, for maximum stable velocity, stable speed, what you need to do is equilibrium or the net force net on the system must be equal to zero, right? This is the only thing which is uh, and what you need to do is maybe take the component of this centrifugal force here, which is nothing but if this is theta, this becomes 90 minus theta and this becomes theta again. So this becomes mv square divided by r into cos theta, and this is the component along the slope and this is the component along the slope. These two forces, uh, see, whatever component is normal to the surface, it will be cancelled out due to a normal force, but the only forces which will not get cancelled out are these two forces along the slope. And for the net force to be zero, these two forces must be equal so that they cancel out each other and the object doesn't skid out of the system. So it means g sine theta must be equal to, or mg sine theta must be equal to mv square by r into cos theta, right? So what we have here is this one cancelled out. You can take it here, and v square is nothing but sine theta divided by cos theta into g into r. What is this equal to? From basic trigonometry, you know that v square is equal to tan theta into gr. So v is equal to under root gr tan theta. This is the speed with which the object should move so as to not skid outwards or inwards in the circular track. I think this must be matching with the whatever was given. Yes, I think it is matching. And when there is friction, this can be the same concept could be used to derive this one, although this will be slightly lengthy. What you will do is basically in this case is this component and this component will remain as such, but the only external thing which will come up is due to a normal force and due to uh, mu as well, which is coefficient of friction, there must be some some friction as well. And for the maximum velocity Vmax, let's say I'm increasing the velocity very much, what will happen is the resultant force will act in this direction, because if you increase the velocity, the centrifugal force increases by v square by r. So if you increase the velocity very much, you will get a high centrifugal force, due to which it will get thrown out of the out of the track outwards, not towards the center, outwards from the center. So what this basically means is the tendency of the object is towards moving the outwards when you are moving towards the velocity maximum, maximum safe velocity. It must mean that the maximum friction which is possible must always act in this direction in this case. And that, what will that be? That will be equal to mu into normal force. How can you find the normal force? This is the component of gravity, and this was the another component of the this force, right? Because you have divided this force into this I think I should use another color for this one. You have divided this force, you have divided this force into this component so as to equal this one, but the other component which you have missed out is this one, right? We had ignored it because initially there was of no use. The normal force was of no use. But in this case, both g cos theta and this one, mv square, by r into sine theta, they will get added up because they are in the same direction, and that will be equal to the normal force. And once you multiply it with mu, you will get the force of friction. What you will basically do in that case is, this force must be equal to g sine theta plus the frictional force which you have calculated from here. And when you solve for that, what you will be left with is these this maximum velocity. All right, I think they have just repeated it here. What's there here, we have already discussed this one. And I think that is all for this mind map. And thank you.